Hello students, in today's lecture we are going to derive the matrix for the refraction of light. So consider the refraction of a ray at a spherical interface separating two medias of refractive indices n and n prime. Let's suppose to the left side of the spherical interface the refractive index is n and to the right is n prime as shown in this figure. We now relate we want to relate the ray coordinates y prime, alpha prime after refraction to those before the refraction, which is y alpha. Since consider this point object, let's suppose a ray of light is going through in this direction and it makes an angle alpha with the optical axis as shown in the figure. So when the ray of light reaches here, at this point the refraction occurs. So similarly, the angle of the ray at this point with the optical axis is still alpha, as from the geometry you can see that this angle is equal to this one. At this point the height of the ray from the optical axis is y. Let's suppose this is y, and this ray has made the angle theta with the normal, and this is the normal, the dashed line. You see that this is the normal at the point of incidence of light. As you can see that this ray of light goes straight to the center of the curvature. So the angle of incidence of the incident ray with the normal is theta, and the angle of the incident ray with the optical axis is alpha, and at the point of incidence or at the point of refraction the height of the ray from the optical axis is y. Now at this point the refraction occurs, and instead of going straight the ray bends towards the normal. The angle of the refracted ray with the optical axis is alpha prime, and similarly the angle of the normal with the optical axis is phi. So here if this angle is phi, so this one is also phi, and similarly the angle of the refracted ray with the normal is theta prime. As from this figure you see that the refraction occurs at this point, and at this point the incident ray, before refraction the height of the ray was y, and after refraction the height of the ray is still y prime. So y is equal to y prime. On the other hand, now we want to find alpha prime in terms of alpha. So from the figure, as y prime is equal to y, there is no change in the elevation, and the angle alpha prime, which is the angle of the refracted ray with the optical axis, you can see from the figure this theta prime is equal to phi plus alpha prime, and theta prime is equal to phi plus alpha prime. From this equation we get that alpha prime is equal to theta prime minus phi, and if this angle is phi, so this one is also phi, and you see that here we have a right angle triangle, and for small angle approximations, for paraxial angle approximations, for paraxial Spherical approximation. Spherical approximation means if the angle of the incident ray with the optical axis is small, in case if this angle is very small, so that means that spherical approximation. Then phi sin phi is equal to, and also if we consider this point from the point of refraction to the center of curvature, let this distance is r, this one is r. So sin phi is equal to, which is y divided by r, y divided by r. And for spherical, in spherical approximation, sin phi is almost equal to phi, so this will be phi is equal to y upon r. That means that if this angle is kept very small, means that if alpha is small, then phi will be definitely smaller. If this for a smaller angle, the sine of the angle is always equal to is somehow equal to that angle. So if we substitute this value in that equation, so this one will be equal to alpha prime is equal to theta prime minus y upon r. Let this is equation number 1. Also from the figure we see that this angle is phi, the angle of normal with the optical axis is phi. So here it is also, this dash line is also can be considered the optical axis, so this angle is also phi. So from here we see that alpha plus phi is equal to theta. This angle theta is equal to alpha plus phi. Also theta is equal to alpha plus phi. Therefore this implies that alpha can be equal to theta minus phi, and phi is equal to y upon r. Therefore alpha is equal to theta minus y upon r. This is equation number 2. Now according to Snell's law, that is n, before the refraction the refractive index was n and the angle of the incident ray with the normal is theta. So n times sine of the angle of incidence is equal to the refractive index of the other hand side and sine of the angle of refraction. So this is sine of theta, which is the angle of incidence, is equal to n prime sine of theta prime. So we assume for spherical approximation, so in spherical approximation sine of theta is also somehow equal to sine of theta is almost equal to theta. Similarly sine of theta prime is equal to theta prime. So that is in the spherical approximation. So this equation can be further written as n times theta is equal to n prime theta prime. So by substituting the value of theta, which is alpha plus phi, theta is equal to alpha plus phi. So we can write this as n times theta is alpha plus phi is equal to n prime theta prime, and theta prime is phi plus alpha prime, or alpha prime plus phi, and phi is y upon r. So further this will be equal to n times alpha plus y upon r, which is equal to n prime times alpha prime plus y upon r. So now bringing this n prime to the left side, this will be n upon n prime times alpha plus y upon r, which is equal to alpha prime plus y upon r. From this equation, the value of alpha prime will be equal to n upon n prime into alpha plus y upon r minus y upon r. So multiplying this term with these two, so this will be alpha prime is equal to n upon n prime times alpha plus n upon n prime times y upon r minus y upon r. Now taking this y upon r common from these two terms, this will be equal to n upon n prime alpha plus plus 1 upon r, 1 upon r into n upon n prime minus 1 times y, or we can write it as alpha prime is equal to n upon n prime times alpha plus 1 upon r times n upon n prime minus 1 y. This is equation number 3. So already we discussed that y prime at the point of refraction. At refraction point, y prime is equal to y. So we can also write this y prime as r y prime is equal to 0 times alpha plus 1 y. This is, let's suppose, equation number 4. Or we can rearrange them as in the book. Y prime is equal to 1 y plus 0 alpha. So there is, I think this one is 5, and this 3 equation will be alpha prime, this one is from 3, alpha prime is equal to 1 upon r into n upon n prime minus 1 times y plus n upon n prime times alpha, this is 6. So these two equations, these are linear equations, and we can now write them in the form of matrix. So in matrix form, we can write it as y prime alpha prime. This is now equal to, here it is 0, this is, sorry, this one is 1, and this is 0, and this one is 1 upon r times n upon n prime minus 1, and here it is n upon n prime. This is y and alpha. So now this is the final equation 7. Here we use a sign convention for r that should be familiar to you. If the surface is instead concave, then r will be negative. Here in the diagram we consider the convex surface, so here this r is positive. If that surface is concave, then r will be negative, so this should be remembered. And also if this r goes to remember, r will be positive for convex and r will be negative for concave surface. And if r tends to infinity, so that will be the matrix for the, then the matrix will be for plane surface, the refraction due to a plane surface. So this equation, this matrix is actually this matrix which is for refraction, so we can write it as r is equal to 1 upon r times n upon n prime minus 1 into n upon n prime. This matrix should be remembered. This is for the refraction due to a spherical surface. Now we are going to derive the matrix for reflection. So consider the reflection at a spherical surface. As in the figure you see that we have considered a concave mirror of radius r. Let's suppose the radius of the mirror is r, and let's suppose this is the optical axis, and a ray of light is allowed to fall at this point, and after reflection it is now going in this direction. So from our previous knowledge we know that the angle of the incident ray with the normal is represented by theta, and the angle of the reflected ray with the normal is represented by theta prime. Similarly, the angle of the normal with the optical axis, let's suppose this angle is phi. So if this angle is phi, so this angle should also be phi, because we have considered an optical axis, which is by the dashed line here. So similarly, the angle of the incident ray with the optical axis, as you can see here, this is the angle of the incident ray with the optical axis. We represent this by alpha. So if this angle is alpha, this should also be alpha with the optical axis, the angle of incident ray, this is alpha. And similarly, the angle of the reflected ray with the optical axis, this is alpha prime, and this, the point where the reflection takes place, its height from the optical axis is y. Now we are going to find the final coordinates, which are y prime and alpha prime. Y prime is the height of the reflected ray from the optical axis. As you see that if this is the height of the incident ray from the optical axis, and similarly the height of the reflected ray at the point of reflection is also y prime. This is the same, this is y prime. So first, now from the geometry, of the figure, also it must be noted that the radius of the concave mirror is considered to be negative, while for the convex mirror it will be positive. And also it must be noted that the angles below the optical axis will be taken negative, and the angle of the angles above the optical axis will be considered positive, as which is explained here in this figure. So from the figure we see that the angle of the incident ray with the optical axis, it is alpha. So if this one is alpha, this alpha is equal to theta with plus phi. So from figure you can see this figure in the book, which is on the page 401. You can see this figure very clearly in the book on the page 401. So from figure, alpha is equal to theta plus phi, which is this angle from here to here is phi, and then it is theta, and this whole angle from the optical axis to the incident ray, this angle is alpha. And for paraxial approximation we have considered this phi, this phi, it is phi, this angle is phi. If this one is phi, this should also be phi. So from this triangle, this distance is y, this one is r, this distance is r, and from geometry we know that sine of theta is equal to perpendicular upon hypotenuse. And here in this triangle the opposite side is y, so this one is y, and the hypotenuse is r. So sine of theta is y upon r, and for smaller angle sine of theta is almost equal to theta, so theta is sorry, this angle is not theta, this one is phi, this one is phi. Phi is equal to y upon r. So we can write here phi, instead of phi we should write y upon r. So this alpha will be equal to theta plus y upon r. As I told you that the radius for the concave mirror should be taken negative, so I have write it minus r, and alpha will be equal to theta minus y upon r, or I can write this theta as alpha plus y upon r. Let this is equation number first. Now alpha prime, this is alpha prime, the angle of the reflected ray with the optical axis, it is alpha prime, and from this figure you see that this is equal to theta prime minus phi. If this one is theta prime, from the normal to the reflected ray, this is theta prime, and this angle is phi. So also alpha prime is equal to theta prime minus phi, and phi can be written as y upon r. Alpha prime is equal to theta prime minus y upon minus r. This negative sign is due to the convention, which is r is negative for concave and will be positive for convex. So this will be alpha prime is equal to theta prime plus y upon r. This is now equation number second. But due to law of reflection, by law of reflection, theta prime is equal to theta. The angle of incidence and angle of reflection are the same. Therefore, this equation second can be written as alpha prime is equal to theta. I have written theta prime is equal to theta plus y upon r, and from equation number 1 theta is equal to alpha plus y upon r. So therefore alpha prime is now equal to theta, and theta is alpha plus y upon r. So this is alpha plus y upon r plus this one y upon r. So this is now alpha prime is equal to alpha plus 2y upon r, or we can write it as, in the form of linear equation, we can write it as alpha prime is equal to 2 upon r y plus 1 alpha. Let this is equation number third, and y prime, which is the final coordinate at the point of reflection, you see that y prime is equal to y, and at point of reflection y prime is same as y, or we can also write it as y prime is equal to 1 y plus 0 alpha. This is 4. Now we can write these two equations in the form of matrix. Therefore this will be equal to y prime alpha prime, which is equal to 1 0, and this one is 2 upon r 1, and this is y alpha. This is equation number 5. So this is our final equation, and this matrix is called the matrix for reflection, and we usually represent this matrix by M. So this is M is equal to 1 0 2 upon r 1, And if r goes to infinity, so in that case the mirror will be plane mirror. So for a plane mirror, this m will be equal to 1 0. This is for spherical mirror, the matrix for spherical mirror. And if r tends to infinity, this will be 0 1. This is for plane mirror. So we should memorize these equations. Thank you very much.